So now that we have established that a linear classifier is quite simple and quite easy to understand, question is, why should we study linear classifiers where the examples that we get for classification, the training samples that we get, need not be linearly separable. So a quick example is that, let's say this is again your x1, x2 plane. This is x1, this is x2, and the positive and negative samples are given in such a manner. So let's say these are all your positive samples. Okay, then you're also given negative samples, but let's say they are on two sides of this set of positive samples. So now I cannot draw any linear hyperplane that can separate these two. Anything that I draw, let's try to draw some hyperplanes. So let's say I draw this plane or whatever plane that I try to draw, it will misclassify some points. Some points will fall on one side where they should not be falling. So it's very difficult, and it's impossible in many cases to actually get a dividing hyperplane. So what is a hyperplane? So if you have, in general, if you have n dimensions, then it's a n minus 1 dimensional surface, a linear surface within that n dimensional space. So for example, in 2 dimensions it will be a line, in 1 dimension it will be a single threshold, a point, in 3 dimensions it will be a 2-dimensional plane with different orientations. This linear hyperplane need not always be able to classify or perfectly divide the positive and the negative samples. So we are not even talking about more complex cases where we have more than 2 classes. We can build classifiers for more than 2 classes by putting several binary classifiers together, but we are not even going there. Even just for binary, it is not always possible to have a linear hyperplane. If that is the case, then why do we study it? Obviously, the reason is that it is one of the simplest classifiers to study, but then also because many nonlinear problems can be linearized. So we saw the example of this when we were studying regression, that we can extract features or we can create features that will linearize the problem. And the other reason to study is that it has some nice analytical properties. It is a natural outcome for some familiar classes of densities, probability densities of the different classes. So I will come to that in a bit. So we will look at these one by one. Okay, so how do we linearize nonlinear problems? We can do several things, such as increase the number of features, or we can extract features that are linearly separable. So for example, let's look at the case of adding new features. So if we look at this particular case where all the positive samples are close to the origin, and all the negative samples are away from the origin, surrounding this. So there is no way to linearize it, but what we can do is we can add some terms, right? We can add some additional features. So this is just x1 and x2 feature, but we can have a derived feature x3. So here x3 is not shown, but let's say I say that x3 is equal to x1 square plus x2 square. Okay, or I can take the square root of that. So if I do that, then basically you will have a third feature. In the third feature, these points will be closer to the origin, and the other points, the negative points that you see, will be further away from the origin. For them, the x3 is large. For the positive points, x3 is small. So I can now have a threshold in x3 that can divide the set of training points into positive and negative labels without any problem. And these positive negative labels could be anything. For example, cats versus dogs, or loan defaulters versus those who would pay the loan back, etc. It depends on the domain. So we can linearize the problem by increasing the number of features by adding new features. So for example, we can add interaction terms, which is we can add variables such as x4 is equal to x1 times x2. or we can add kernels, for example the one that I just showed here. So there are different ways of adding features that can linearize the problem. Another way to linearize the problem is to use pre-trained neural networks. We will come to that in a bit. Okay. So suffice it to say that learning linear classification is important because with some underlying nonlinear feature extraction or feature creation, we can actually solve problems in a linear manner. Okay. Now let's look at how the linear classification becomes a natural choice when we make certain assumptions about how the data was generated. So before we do that, I want to show you a model of data generation. So let's say we have two classes, and the classes are, let's say, cats versus dogs. So I will just call them C1 and C2. Okay, so I have class C1 and I have class C2. Okay, so let's say this is cats and this is dogs. Right. And because and for these classes I am going to extract, I will measure some features. For example, let's say slant of the eyes, or the size of the relative size of the nose compared to rest of the face, and so forth. And based on that, I should be able to classify between cats and dogs. So I have a class variable C, and this class variable can be either C1 or C2. Right. So given this class variable C, okay, I will draw a graph. So graph has vertices and edges. It's a directed graph, and based on that I will generate the variable X, which is what I measure. And let me make it bold because it's a vector. Okay. So this is class Ci will generate Xi. So what that means is, first I toss a coin, and when the coin shows tails or heads or cats or dogs, based on that I generate a picture of the or the feature vector of the cat or a dog. Okay, so that's a generative model, and we assume that the world works that way. However, what we are interested in is not the generative part, we are interested in the discriminative part. That means given X, what is C, right? So basically what we are interested in is that we want to find out P of C given X. Whereas the way the world works, or the way we can easily model the world, is to have a prior probability over C. That means what is the relative prevalence of cats versus dogs, and given the class, how do the features of the cat or the dog look like. So what is P of X given C, right? So how will we do that? So let's say we are given a training data. We separate the training data into cats and into dogs, and we form a model of what does the distribution of X, if it was taken only for cats, looks like. What is the distribution of X given only if we look at the dogs looks like. And based on that we have P of X given C. So P of X given C is equal to 1, P of X C given C is equal to 2. All right. So now we want to reverse engineer, and we want to find what is the probability that given a feature vector, whether that is coming from class 1 or class 2. So we will use Bayes' rule of probability. What we will say is that it is P of X given C times P of C, right, and divided by P of X. Right. So in other words, what this is it is likelihood times the prior divided by the evidence. So what is the evidence? Evidence does not change between class 1 and class 2. It is what is given to us anyway. So what we are actually trying to do is we are trying to measure the ratio of the two classes, probability of two classes given the data, which is we are trying to measure P of C1 given X divided by P of C2 given X. And this division we are going to measure whether it is greater than 1 or less than 1. If it is greater than 1, then we can make a decision in favor of class 1. If it is less than 1, then we will make a decision in favor of class 2. And so this is going to be P of what is the likelihood that the data was generated assuming class 1 times the prevalence of class 1 divided by what is the likelihood that the data was generated assuming class 2 given prevalence of class 2. So why are we using the prevalence? Because it's possible that if we want to be overall right, we might want to bias our decision in favor of the class where more samples are present. Right? This does not always work out because sometimes the risk of misclassifying one class versus another is greater. So for example, if we are looking at cancer screening, then missing cancer might be a bigger risk than calling someone a false alarm that someone has cancer, because if we miss it, then we will not treat it. If we falsely find cancer in people, the only thing that we might do, the cost incurred would be that we will waste their time, we will waste their money for additional tests. So depending on the situation, it's not always the case that this is the best way to make a decision, but assuming that we have equal risk for both classes, then one way to minimize your risk of misclassification would be to also take into account the prevalence of classes. That's why we have the prior also there. We have P of C1 and P of C2 also in the decision criteria, and we will compare it to 1. Now let's we said that this P of X given C, the likelihood is easier to model. Let's see how that might be the case. So let's assume that this X that we knew that we were trying to use in the previous slide, it has two dimensions, x1 and x2, right? And let's say we take all the samples from class 1 and let's say their mean falls somewhere. Okay, so this is the mean mu1, and let's say the mean of all the samples from class 2 falls somewhere else, and we will call this mu2. Now, so let's call this, I will use two different symbols. So let's say this is the plus symbol and this is the circle symbol. So a decision boundary could be that, let's look at this mu1 and mu2, draw a line that is going from mu1 to mu2 and bifurcate it and draw a normal from that. So that could be a simple decision rule. So let's change the color a bit. So let's say I want to draw this line and then draw the normal at the bisector of this line segment, and this will be my decision boundary. So decision boundary is where I have an ambiguity whether it is class 1 or class 2. So we won't take degenerate cases. We can always have a arbitrary rule to classify between class 1 and class 2 if the point falls exactly on the decision boundary, but the probability of that is 0. So what we will assume is that we are not worried about the decision boundary. We are only worried about points falling on one side or the other side of the decision boundary. So here a simple decision rule could be that anything that falls closer to mu1 is going to be classified as class 1. Anything that falls closer to mu2 is going to be classified as class 2. So here this 1 and 2 is not the dimensions, these are the classes C1 and C2. However, is that optimal, and is the decision boundary, should it always be linear? So that now let's look at that little more carefully by making some assumptions on the decision boundary, on the class conditional density. What is class conditional? That is the probability distribution of x as a vector given, let's say, class C1, and the probability distribution of x given C2. Okay, so let me erase this because I don't know whether it is ideal or not, and let me change the color of the second distribution and use a different color. So P of x given C2. All right, so now let's look at P of x given C2, and let's assume that these are dogs that we talked about and C1 is cats. Okay, so this is mu2. So let's assume that this is a Gaussian distribution, and the Gaussian distribution, its equal probability contours look like this. On the other hand, if we look at mu1, Let's change the color a bit. So this is mu1, and let's assume its contours of equal probability look like this. Okay, and they are both modeled as Gaussian distributions, and as you know that the Gaussian distribution, its contours are going to be elliptical, and the slope of the ellipse depends on the covariance matrix. So what is the formula for the class conditional distribution? So P of x given Ci, I could be 1 or 2, okay, is going to be, and I'm going to do this in d dimensions, one over 2 pi to the power d, okay, determinant of the covariance matrix square root, okay, and then we will have exp, and let me just put it here in the numerator, exp, and here I will have minus half x minus mu I, or let's use j for class, I for sample point. So x minus mu j, okay, transpose sigma inverse x minus mu j. So this is an n-dimensional Gaussian, okay, and this j can be either 1 or 2, and based on that we will get, if we want to draw contours of equal probability, we will use different constants to generate the ellipses that you saw in the figure, the red ellipses and the green ellipses, okay, and depending on the covariance terms in sigma, you will have a right tilt or a left tilt or a no tilt, etc. Okay, so this is the general setting, and in this general setting we want to match, for finding the decision boundary, we want to match p of x given c1 times p of c1 with p of x given c2 times p of c2, and in general that boundary is not going to be linear, that boundary is going to be some quadratic boundary, okay, some boundary we will get for that, but we will see that for certain cases it actually turns out to be linear. So before we get there, let's look at this case a little more carefully. So we have, let's use a brighter color. What we want to look at is p of x given c1, p of c1 divided by p of x given c2, p of c2, right? And we want to compare this with 1. Instead, what we will do is we will take the log of this and compare it to 0, okay, which is basically the same thing. So what we are going to do is we are going to compare log of p of x given c1 plus p of c1, or log of p of c1, minus, right, so this minus log of p of x given c2 plus log of pc2, and we will compare this to 0. If it is greater than 0, then we will make a decision in favor of c1. If it is less than 0, we will make a decision in favor of c2. Okay. So this is the general setting. Now you can see where I'm getting at. So we want the certain terms to cancel out, and those terms can cancel out for a particular case where, so let me go back here. This was actually, there was a index j here, okay, that is for the jth distribution. So this one has sigma 2 and this one has sigma 1. So going back here, you can see that this the constant that you have outside, right? So this constant that you have, this constant can cancel out if sigma I and sigma j are equal. Okay, so that is an assumption we'll have to make. It may not always be true, but if sigma 1 and sigma 2 are the same, that means the contours are shaped the same way, they are tilted the same way, and they rise the same way, then we can not worry about this constant, because you will take the log of this constant on, and they will cancel out because of the negative in between, right? All right. So in case when the variance are the same, so basically the decision that we have to make is the log of let's look at p of x given c1 plus log of p of c1 minus log of p of x given c2 log of p c2, right? So here this will be equivalent to the constant will vanish from both sides because of the negative sign, and what we will get is log of the exponent, which will give us minus half x minus mu1 transpose sigma 1, sigma is the same for both, so sigma inverse x minus mu1, right, plus this is a constant c1, I will just call it constant k1. Okay, so this term is k1, and then minus similar term for with mu1 and sigma, right, x minus mu2 transpose sigma inverse x minus mu2, and then minus k2. Okay, so what we can see is that this is going to be a straight line, because we made the assumption that sigma 1 is equal to sigma 2 is equal to sigma. This is the assumption. Okay. So this assumption, only because of this assumption, it works out that we will get a straight line. In general, we will not get a straight line. We will get some sort of a quadratic curve, as you can see from this expression, if I plug in sigma 1 and sigma 2 separately instead of sigma. So what this means is that if I draw the x1 x2 plane, right, and if I draw the class conditionals, they can be of any shape. So they can be of any shape as long as they have the same shape for both classes, and the same tilt for both classes, and one of these can be raised up, one of these can be raised down because of the prior. That means p of c1 and p of c2 need not be the same, they need not be half and half. Okay, just that one of them can be raised up, one of them can be can be pushed down, and yet the boundary that I will get will always be a straight line. That straight line will be at the bisector of mu1 to mu2, but its tilt need not be at a 90-degree angle. It need not be normal to that bisector because of the tilt of the ellipses that you see, the contours of equal probability that you see. So depending on the tilt of sigma, these two can this angle need not be a 90-degree angle. Okay, but it will be a straight line. So it again depends on a assumption that sigma 1 and sigma 2 are equal.